What is power electronics?
So power electronics is basically transforming one way of electrical power into another way of electrical power. So for example, from going to AC to DC, or DC to AC, or DC to DC.
Whatever that is process of energy, electric energy, into a form or another, is processed by a power electronic system.
From laptops, mobile phones, etc., all the way to big ships, and very large aerospace applications, etc. So it caters to a wide variety of applications as well.
But you also have solar inverters, at wind turbines you have power electronics, and of course in electric cars you also have power electronics to transform the energy in the battery to the energy in the motor.
So whatever that is electric energy be used, that energy has been processed by a power electronic system.
So it's about the design of converters, inverters, not only from the hardware point of view, but also the software point of view. So you can also learn, for example, or focus on the control of the power electronics itself. So there are different paths that you can take.
I really like building stuff, so with power electronics you build converters. So that's a very nice way of doing practical things. But also during my bachelor I was part of Green Team Twente, which is a student team that built a hydrogen car. And I think there, because there I designed some power electronics like motor control, energy storage, I think there my interest for power electronics really developed. I think it's because you deal with quite high power stuff usually, so like kilowatts, and you actually build something which is like relatively big. So compared to, like, for example, chips, which are relatively small, you cannot really see it properly, you need a microscope, but with power electronics you can really have the converter in your hands, you can really probe things easily, you can really play around with it.
If you are a student in electrical engineering, you have to follow 2 mandatory courses.
2 courses in ethics and philosophy, and there you sort of learn how to be a good engineer. So what impact your technology has on society and how you can have a positive impact on society as well.
And especially for the power electronics, there are 3 mandatory courses.
Power electronic converters, we have energy conversion, people, plan, prosperity, and we also have advanced power electronic systems.
First of all, we start with the power electronics converter course, right? It's very important because we study different circuitries that drive for different applications, right? So there you understand how to design converter using your charger, for instance.
Actually, it enables you to be able to learn the basics of power electronics through the course of power electronic converters, which is given by Professor Thiago.
Which is basically a course on basic circuit topologies and also the elements you have, like capacitors, inductors, and how you use those to transform one way of power into the other in another way. And we also had a lab during that course. And there you work on a boost converter. So a boost converter is basically that you transform a lower voltage into a higher voltage. Both are DC. A buck converter is the opposite. So you go from a higher voltage to a lower voltage. And then you also have a buck boost converter, which is the combination between the two. So you have a fixed input voltage and you can go higher or lower.
We do have the PPP course, and that also tells you about what the needs and to use energy wisely, right? Not only for the perspective of energy efficiency, but also the social impact of availability of energy.
And that is basically a multidisciplinary course where you work on power electronics, but also on the impact power electronics, for example, can have in the third world. So you can work on projects like electrification of Africa.
Another course is called Advanced Power Electronic Systems.
And that was a really nice course because there you get it's sort of a project course, and you get coupled with people from industry, with companies.
So to give an example, we have lecturers from ASML, Philips, Alphen, etc., etc. So a lot of big companies in the field of power electronics who actually come and deliver a lecture. and the students take part in a challenge, a design challenge, which runs through the entire quarter, where they come up with solutions to real problems that's in the industry. For example, within the problem that was defined by Alphen, they had case studies which reflect upon what should be the size of batteries which should be installed in the grid, which can perform ancillary services, services that can help the grid to maintain the voltage, maintain the frequency, etc. And students came up with trying to find innovative solutions for what should be the energy level that battery should perform at, what should be the power level, and how does the grid manage stability. We call this grid codes, so you will get an opportunity to learn all that.
Yeah, you learn a lot about industry, you learn a lot about problem solving. That course was also really interesting.
We have 2 tracks. So one track focuses on power devices, where you might choose the course Power Semiconductor Device Physics. And for the track of, let's say, Power Electronic Systems, you will choose Electrical Machines and Drives.
And then we come to the device physics, that power devices is at the heart of power electronics. So devices are the one that we use to convert energy. So these devices, they need to be very efficient. And there are different technologies there. And it is a strong evolving technology, so our course adapted every year.
And then I also did a course on electric machines and drives, and that basically is on motors, on generators, and all of the different types of motors you have and how they operate. So it's like sort of the interface between the electrical world and the mechanical world.
So electrical machines are, those equipments that actually transform electrical energy to mechanical energy or vice versa. And of course, to be able to perform or to make the electrical machine perform optimally with highest efficiency, you also have a power converter in between them. That combination is then called drives. Electrical machines and drives deals with applying fundamental theories like Maxwell's equation to different types of machines, AC machines, DC machines, and different types of special machines. For example, in our laboratory, one of our students is currently realizing a setup which is then a Ward-Leonard system which connects an induction machine with a brushless DC machine, which you can then use to make a couple. And you can use a machine as a motor and the other one as a generator, or vice versa.
And then you can characterize the machines, you can calculate the power efficiency. So that is also one of the targets of that setup, that students, they get hands-on experience with machines and also with how to drive those machines, what do the waveforms look like. That is the nice thing about that, and it's also very high power stuff, so that's also pretty cool to work with.
We do see it a strong need yet for new courses to be created. I'm very excited.
So that will be on the topic of smart grids, which my colleague, Assistant Professor Nataly Banol, is taking care of.
And in that course, you will learn first how the traditional grid used to work, then how it evolved to a smart grid, so all the smart devices that we have connected because all this energy transition. Then you will learn how to run a power flow, which is very important for electrical engineers. So you will learn how to use Panda Power or OpenDSS, which is the software that we will use to run these simulations. And you will also learn how to develop the power flow yourself, so all the equations, the dynamics, etc. Then you will learn how to model smart devices, let's say batteries, heat pumps, electric vehicles, solar panels, etc. You will learn the dynamics, very detailed models about this, and then you will learn how to integrate these devices into the electricity grid and putting everything together.
Of course, you have like the mandatory courses, which gives you like a solid foundation of, for example, certain converter topologies. But what I like most is the things that I could do like next to my studies. So, for example, you have a Capita Selecta course. So, Capita Selecta is basically that a student can come up with a proposal to do a certain project. So what we did is we participated in a design challenge, and then we used that design challenge to also get some ECs. And that design challenge was about wireless power transfer, so transferring power wirelessly so you don't need a cable. It's used in a lot of places, for example, with your phone, if you have wireless earbuds, there it's used as well. What's interesting is that it's very physics heavy, so you deal with a lot of magnetics, for example, because in the end you use electromagnetic waves to transfer power instead of just cables. So it was fairly interesting to work on that.
We also have courses that actually enable you to look at power semiconductor devices. So Associate Professor Raymond Huting teaches the course Advanced Semiconductor Device Physics.
I also did systems engineering, so that is more of a high-level course where you look at the whole system and you look at different subsystems and how they interface. Yeah, and that can be also very beneficial if you, in the end, are going to design electronics. You really need to know things about the system as well, like the higher view.
What are some of the real problems that you worked on in that course?
So I worked on converters for space applications. And there are very strict requirements on how much noise a converter can produce, because in space you have very sensitive electronics to do measurements. So also your converter needs to be, like, sort of say, quiet, so that it doesn't interfere with those sensitive electronics.
But you're also free to choose other electives for the rest of the credits that you need, 60 credits from, a wide variety of courses that Twente offers, So there's quite some flexibility in the program as well.
Power electronics is used to process energy, right? So sometimes when you do research in solar or wind or in batteries in general, we are processing energy. So in our laboratory, we develop the power processor, the power electronics part, but we need to have, for instance, emulators, right? We don't have the solar panels there. We buy sources that can emulate the performance of a solar cell. Of course, we also have a battery laboratory. In the battery laboratory, we need to, because one of the objectives is to do smart BMS systems, battery management systems, then we need to be able to monitor accurately the current voltage and temperature of battery cells. We also need to have thermal chambers. We need to control temperature of components, right? Because we want to check reliability of components. So we need to be able to change from minus 40 degrees until high temperature.
In the first year, you have to follow the courses, all the courses, and then in the second year, you can do an internship the first half of the year, and then you have the master thesis.
What are some examples of projects that come out of the Power Electronics Master?
Yeah, we do different applications, right? We focus mostly in electric transportation. So we have topics in maritime, for instance, so how to change the microgrid inside a maritime vessel. For instance, the develop of the converters that you use to extract power from battery, right? We think about future electric ships. So how to optimize this converter, how to make sure that the system is processing the power in an optimal way, how to make the system compact.
In my internship, I worked at Nataly Power, which is a company that designs wind turbines, but they're relatively small. There's like 1.5 meter diameter. And for that wind turbine, I developed electronics to basically get the power from the wind turbine and feed it into the grid. So that's basically going from AC to DC and then to AC, which the grid requires. That was really cool. I learned a lot. I had a really nice supervisor, but also had good supervision from my professor. Yeah, and in the end, I actually built a converter. So that was also pretty cool. That was like one of the first real sort of professional converters that I designed.
Last year I had a student who did an internship in Avia Volt, which is an EV charging company, let's say. They have a special charging infrastructure for EV trucks, and EV trucks are like huge cars that need a lot of energy. So this student actually developed an energy management system for that location. So, for example, what kind of battery, what is the size of the battery. There is also solar panels. There are also solar panels in the site, on site, on the place. And you have to manage the electricity flows between all these assets, right? So the student actually developed this energy management system.
And after that, they go to the master's thesis.
For my thesis, I did research on an inverter for high-speed compressors. So in aircraft, you have a compression system to keep the cabin of the aircraft compressed. And that spins at a relatively high speed, so you need a very specialized converter to basically convert DC into a high-frequency AC, which then drives the compressor. And then the focus was on efficiency and making it more lightweight. During the courses you have very basic converters, so you go from like DC to DC, like a buck or a boost converter. So that's still relatively basic, but then during my master thesis I did a lot on inverters. And I learned a lot of things about inverters, what topologies are there and how to control it, because control is also a very important part of power electronics. You really want to control all of the voltages, all of the currents, otherwise it can be unsafe and things might blow up.
Has anything ever blown up? You worked on?
Yeah, especially during the bachelor.
I have a student that is working on the co-simulation of power systems and power electronics. So we have a real-time simulator in our lab. And what he's trying to do is to connect two different softwares. Let's say OpenDSS, which is a software that is dedicated to run power flow calculations, so it's more dedicated to the big electricity grid, let's say, a distribution system. So where is the transformer, where is the connection to the main grid? We have different nodes, which could be like the consumption, so your house or a company or the university itself. And then we have some smart assets, let's say batteries, or we have PV, solar plants. We know that in the Netherlands now we have a lot of specific solar plants, and they are like distributed all over the country. And then we see how these two things interact each other and how can we improve, for example, the operation of the grid. So if you have, what we want to avoid is to have blackouts, for example. So we don't want to run out of electricity, right? We need it, otherwise we couldn't be here recording this. But if we don't do it in the right way, we might have some problems and maybe have some shortage of energy. So we try to find ways to avoid that.
During your internship and your master thesis, you can really excel. So if you choose an interesting topic that you really like, then you really get the freedom to do what you want.
As far as I know, most of our students get top jobs. It is a topic that is very relevant for the society. And because it's very relevant, there are plenty of jobs, which is very interesting.
If you finish your master, you can go to industry. There are plenty of opportunities here in the Netherlands, but also in Germany. And you can also go to do a PhD, for example, here at the University of Twente, but also abroad. So there are plenty of opportunities, plenty of jobs in this field.
Tesla, for example, in Amsterdam, some of our students who work there. We also have students who are in this region as well, you know, in DEMCON, in VDL energy systems. We also had students who work for ASML, ProDrive, which is a company that delivers cutting-edge power electronics to ASML as well.
You can go directly to grid operators, like for example, Alliander, Enexis, Stedin. All those are grid operators. You can also go to the transmission operators, which are, for example, TenneT. But you can also go to any renewable energy company. I know many people that, for example, work on Alfen, which is a company that work with energy storage.
These days, renewable energy is really hot. Of course, we need to reduce the emissions of CO2. And power electronics is almost used in all of those new technologies like wind turbines, solar energy. All of those technologies use power electronics. So there are plenty of job opportunities.
So I think the program is fascinating in the sense that it teaches you about power electronics, it teaches you about electrical machines. It also will have a flavor on power systems and on energy access. So it's quite broad from that point of view.
I learned a lot. yeah, because when I started the master, I didn't know that much about power electronics, and now looking back at it, I now know how to build, for example, a converter. I know a lot about different types of converters, so that, in the end, the master is very useful in the sense that you learn quite a lot of things.
If you do power electronics, you have the chance to actually transform the world and to contribute to the energy transition. The energy transition cannot happen if we don't have technologies that support that. And since I study engineering, I always like to optimize things, and I think the electrical engineering gave me that possibility. And in the power electronics group, I have the opportunity to transmit this message and to convince people to contribute to the planet as well. So.
Learn more about this electrical engineering specialisation by clicking the link in the description, or watch our YouTube playlist to learn about which other electrical engineering specialisations we offer.